necessarily on the probably about ready.
All right, good morning everyone. I'll be making these announcements again because I guess attendance is currently a little bit low. People are still rolling out of bed after a long hike yesterday. But just a few quick announcements. So as you may have heard, there are now suspected MERS cases in Hong Kong. We'll just try to be a little bit careful. Yeah? So there'll be bottles of hand sanitizer at each table during lunch. If you want to keep your hands clean, especially since you've been taking you around Hong Kong, just watch your hygiene. Yeah. Separately, also, so there's a slight change in the schedule today. I noted, talking with many of you over the last few days, you said you enjoyed the social activities, but we weren't giving you time for the primary purpose, to talk to each other, to have discussion and so on. So today, we will still be having the banquet dinner in Chim Sa Choi, but we will not, we won't go walk around before. We'll just be going for dinner and then coming back. So we'll leave here later than usual. We'll leave here at 6:30. So in between, we'll be building in time for you to have more relaxed interactions with each other. Those will take the forms of some slightly different things that are currently in the schedule. I'll give you more details in the afternoon just before lunch. All right. All right. So not to take any time away from Professor Emre Telatar, distinguished speaker for the day, he's going to be talking about polar codes, which have already been introduced, I noticed, in some of your talks. So I'll hand it over to Emre.
Thanks very much. First of all, thank you for inviting me, also for Chandra, and taking such good care of me, and also tolerating my difficult email response times. Very kind indeed. Thank you very much. It's very nice to be here. So let's see. This will be mostly a Blackboard talk. I may use a computer from time to time just to show you a few things here and there. Voilà. So if you're too far away, you may actually want to be closer to see what is being written on the Blackboard. But it's up to you. But I mean, you don't have to either. So if you're more comfortable there, please stay where you are. We will. Okay.
Will you need that one?
Sorry?
Will you need that one? I can also whiteboard.
That's okay. Will be okay. So let's see, maybe I should say a few words about, I guess if you look back into the 1950s and 60s, you'll find lots of information theorists who are also coding theorists and vice versa. I mean, think of people like Elvin Berlekamp or Jim Massey. But I guess in the intervening years between then and now, our field has split more or less between people who do random coding to prove existence theorems and those who actually come up with more structured objects, typically from algebra, who then try to construct codes which try to achieve what the random coding arguments promise. I guess in the recent years what we have seen is a sort of a re-merging of the two standard paths. And I think polar codes is one of the later steps in this development. It's sort of nice because it's a constructive construct, but it is very firmly rooted in the information theory and probability theoretic fabric of the information theorists. So in a sense, when I teach information theory these days, I introduce the polar codes at some moment, because when you're teaching, say, the source coding part of information theory, it is very natural to introduce things like the Huffman code and then later on the Lampeter algorithm to come up with, yes, okay, here are particular methods we do to achieve what is promised by information theory. But when you then come to the channel coding part, you typically do is you would do a random coding argument first, and then to show the existence of good code. But won't be able to come up with any particular, here is an example of this code, was difficult. With the polar codes, you can actually do this, and the students tend to appreciate this. So what I'll do today is maybe, I guess, is a bit superficial of, I guess, what I typically cover in my own course when I teach information theory to the students at EPFL. So with that, maybe I should start saying a few words about channels and what we're going to talk about. So the object of the study, the polar codes I'll talk about, are going to be for binary input channels. So we're going to have, using the notation from Vincent, I'm going to deal in channels by W. So W is going to be a channel whose input output is going to be the binary 0, 1 back things. I write here F2 on purpose, not just 0, 1, because I'll be using the additional multiplication which is defined in this field to construct these codes. So the fact that the 0, 1 is equipped with some sort of algebra is going to be important. And the output is going to be arbitrary. So output alphabet Y, I'm not going to assume anything about this. Okay? But let's say it is discrete. It doesn't need to be, but let's say it is discrete. So it is specified by two things, the W of Y given 0 and W of Y given 1. These things completely characterize what this channel is. I should also apologize, by the way, for my voice today. I seem to have managed to stupidly contract some sort of a flu, not to help the nurse. So I have a voice which is much more bass baritone than usual. I tend to be a tenor baritone, so I can sing with the deep areas of pen to the fire. All right. So these two things characterize the channel. So now, the thing you notice when you have binary input channels are that there are two classes of easy channels. Okay? So if your channel had, for example, zero capacity, okay? Suppose your W was such that the output had nothing to do with the input. Suppose you had this relationship to be true for every Y. Okay? So W was such that if this were the case, then this channel, obviously you cannot do anything with this channel. The output is decoupled from the input. Okay? So zero capacity is very easy to communicate optimally over, because the optimal thing you can do is rate is 0. So you can achieve capacity very easily for this channel because the capacity is 0. Okay? So now, the other kinds of channels that are easy are the channels for which the output determines the input. So for example, if any Y, suppose it can be achieved from only one of these inputs, either 0 or from 1. The other possibility is that let me write it like this. So this means that for each Y, there can be at most one input symbol which can reach it. Okay? So each output symbols can be reached from at most one particular input. In this case, the capacity is 1. Right? Because right? So it's also easy because for this channel you can have a code of block length 1. Okay? Namely, you map the message 0 to input 0, message 1 to input 1, and the output determines what the message was sent. So this is also easy. Okay? It's also achieve capacity. Now, I guess fortunately for us, the typical channel is not like this. If all channels were of these two kinds, then the communication people will be out of business, because there will be no need for us to be doing anything. Communications will be a trivial problem, okay? So there will be no need to study anything. So typical channels don't belong to any of these particular classes. But let me call these classes to be the easy channels, okay? Or if you wish, the extreme channels. So these are the really bad channels, these are the really good channels. Maybe I should say a few more words about this particular case. So it's not obvious if this is really easy or not, okay? Because for example, suppose you had a channel for which if the input is 0, the output is a uniformly distributed on the irrational numbers, whatever this thing means. Okay? And if the input is 1, the output is uniform on the rational numbers. Okay? Now, to look at the decoder of this channel would be a very difficult job to do, because you receive that you're y. Okay? You decide if this y is rational or irrational. So even though this is easy, okay, it does not. The decoding is easy. Okay? So we'll worry about this thing perhaps later, perhaps never. But I should say that I'm slightly cheating you when I say here this is an easy channel. Okay? So you should be careful about what you mean by easy. This kind of question will never appear when we have a discrete output alphabet y, because then it is discrete, no problem. But if we have a continuous input channel, you should worry about whether having a capacity 1 means that it's easy. This is not really a trivial implication in the case of a continuous output alphabet. Okay. Good. Now, the thing about polarization or the polar code is that you want to transform a channel, or rather multiple uses of your channel, W, to a collection of easy channels. You want to make sure that after you do this transformation, you'll only end up with channels of either close to being this type or close to being this type. Okay? So you want to come up with channels which are either good or bad. Of course, there's a trivial way to do this. You give me a channel W, input is the binary stuff, output is the y. I will map all the outputs to a particular symbol y0. Okay? The corresponding channel will be trivially easy. Okay? But that's not the point. The point is to do this transformation such that you don't lose capacity. Okay? So this is the goal of depolarization, is to transform a given channel W into the easy classes, but while doing so, to preserve the total quality of the channel 2. You don't want to do this transformation in stupid ways in which, yes, you can create easy channels very easily, but those are you'll end up with zero capacity at the end. That's not the right thing to do. Now, we will see how to do this by this polarization. Okay. Do you hear me, by the way? Yes. And also stop me whenever you like. I have no notes. I have just talking like this, so we can talk about something else. I will not object. Okay. Good. Maybe I'll take this one down because there are a few things I may want to leave on the board. It's okay. It's okay. So I'll make use of a basic transformation in this. Okay? So the basic transform I will have is the following. I'll take 2 copies of W. With x1, x2 being the inputs to these 2 copies, y1 and y2 being the outputs of these 2 copies of the channels. That's the 2 copies of the original channel that I have. Independent copies of this channel. So these two channels operate independently of each other. Well, I'll do the following. I will put a modulo plus modulo 2 addition operation. And I'll do this pre-processing at the input side. So I'll take a binary pair U1, U2, map it to a binary pair x1, x2. So clearly, so this transformation is the following. So x1 is U1 plus U2. When I write plus signs, this is the modulo 2 addition if the symbols that I have are the field symbols. Okay? When I write the summation of mutual information, put a plus sign there, that's a real addition. Okay? But if I had a chain rule for mutual information, put plus signs in between, that's a real plus. But if I have binary objects, I'll put a plus sign to mean the modulo 2 plus x2 is equal to U2. Okay? Or of course, equivalently, I can also write the U1 and U2. U2 is obviously equal to x2, and U1 is equal to x1 plus x2. Okay? So if I sum these 2 things up, I get U1 back because U2 plus U2 is 0. Okay? So this is a one-to-one invertible operation that I put in the input side of this channel. So this is not doing anything. Okay? It appears that what I have done is nothing. So it is not obvious if I can gain anything from this particular construct here. But let us see what we have really done. So what I'll now say is that I have created two synthetic channels. Okay, so there's one synthetic channel by this transformation, which is going from the channel U1 to Y1, Y2. I'll call the synthetic channel to be the channel W minus. Okay. The reason for this minus sign will become obvious in a second. All right. The other synthetic channel is the following. It's the channel W plus. That is a channel from U2 to Y1, Y2, and U1. Now, do you see a problem with these two channels? Maybe I should ask you, do you see a problem with W minus? So the channel whose input is U1, the output is Y1, Y2. 1, Y1, Y2. Is this actually synthesized by this construction?
It's not specified.
U2 is not specified, but suppose it is a uniform quotient. Suppose I choose U1 and U2 as uniform 0, 1. So in that case, your objection disappears, and indeed this is a perfectly legitimate synthetic channel. But what about W plus? Is this really synthesized by this construction? Does the receiver who is listening to the output of these W1, W2s, two Ws, does it get to observe U1? No. So clearly, I haven't quite synthesized the channel W plus. So for this, let me now